vectors that you compute, if their dot product happens to be 0, but the vectors themselves are non-zero, so they just turn out to be orthogonal. So what happens here is, well, the iteration can't continue, because if this is 0, then these have to be one, at least one of these has to be 0, and then you're just going to divide by 0 in the next iteration, so you're done. In symmetric Lanczos, these two vectors are the same, so this can never happen. The only way that so this is a 2 norm squared. So what happens is, the only way it's going to be 0 is if this vector is 0, which is actually a welcome event, because we've actually generated an invariant subspace containing eigenvectors, and your iteration can converge immediately. But if series breakdown happens, your iteration stops, and you don't have enough useful information to get a decent solution to your system AX equals B. So this is one reason why unsymmetric Lanczos and any methods based on it tend not to be used very often. People might find GMRes more robust because it has no counterpart to this series breakdown. Okay. So the people don't like unsymmetric Lanczos very much for this reason. Okay, but let's see this through. Now that we have these bi-orthogonal bases for Krylov subspaces based on A and A transpose, how do we use that to solve AX equals B? So to solve AX equals B using unsymmetric Lanczos, alright, so what we do is we assume that X has the same form as we have in all the other iterative methods. It's a linear combination of your cubes. So our goal is that our residual, Rk, which is B minus A xk, is orthogonal to all the columns of qk hat. Now, in conjugate gradient, we wanted the residual orthogonal to all columns of qk. But now we're going to use qk hat instead. So that's the main difference between conjugate and biconjugate gradient. So what that means is qk hat transpose times this residual. And I'll fill in the form of xk here. So that's qk yk. And we want this to be equal to 0. So I'll go ahead and multiply this out. So that's qk hat transpose b minus qk hat transpose aqk yk. That must be 0. But b is the normalized in some sense is the first column of qk hat. So this is actually gamma naught E1. I'll use a bi orthogonality. B is equal to beta naught QK E1. That's beta naught I really want to use because taking dot products of QK hat with QK gives me identity. And then QK hat transpose AQK, that's TK. That comes from a definition of all those entries of this tridiagonal matrix. And then I have YK like before. Now, QK hat transpose QK, that's identity. So, all I have to do is solve this system. TK YK is equal to beta naught E1. So that is how I construct my solutions to my system linear equation. So once I have this YK, I can then use that up here. So all I have to do is put this into my unsymmetric Lanczos. So I go ahead and solve this tridiagonal system. So because it's tridiagonal, this is very easy to solve. It's only going to take order K floating point operations. Now, so this amount of work is negligible compared to what else is happening in iteration, because in unsymmetric Lanczos, you're doing matrix vector products, A and A transpose. So that's order n squared work, or maybe somewhat less if A is sparse. So this is still much less work than GMRes is doing from iteration to iteration, because that's working with solving a system involving a Hessenberg matrix whose upper triangle is going to be full. A lot more work. Okay. Now, so what you can do, is, now, recall when I presented conjugate gradient. I first presented the Lanczos algorithm, and I described how you can solve this system like this to get your solutions. But this did not have an easy way to obtain each new solution from a previous one, like a typical non-stationary iterative method. So I did all these really ugly manipulations to get iteration of that form, and that's conjugate gradient. So you can do the same kind of manipulations that produce conjugate gradient. You can apply that to unsymmetric Lanczos to produce the biconjugate gradient algorithm. So I will quickly show that, and then we can wrap up discussion of non-stationary iterative methods. Okay, so at long last, here is the biconjugate gradient method. We're solving in general AX equals B, so square invertible, but not symmetric, not positive definite, anything like that. Okay, so our initializations, K is 1, we have our first residuals, R1 and R1 hat are both equal to B. And then our initial guess from a solution, we'll just use 0. And then we just keep going until we achieve convergence, if we do. So for K greater than 1, we need search directions, just like in conjugate gradient. But we're actually going to have two sets of search directions, one for A, one for A transpose. So I have a parameter UK. This actually appeared in the conjugate gradient method. And the formula for it is exactly the same, except here, notice in both dot products, the vector on the left side is going to be one of the hats, which we're going to see all through the algorithm. So we get rid of the hats. This exactly this just reduces to conjugate gradient. So now I have my two sets of search directions. So PK, like in conjugate gradient, is RK pk times the previous search direction. And then I have a second set of search directions, pk hat, based on my hat residuals. I'm using the same parameter, uk for both. Otherwise, I'll just set both initial search directions equal to R1, which is just B. So that's how I set my search directions. And then the main work in this algorithm is right here, just a matrix vector multiplication. And then from there I get a parameter that I need, just like in conjugate gradient. So again, if you take the hats out, it just reduces to the conjugate gradient formula. Okay. So one issue is because A is not symmetric positive definite, this is pk hat transpose APK. When it's symmetric positive definite, that quantity is guaranteed to be positive. You don't have that guarantee anymore. So now I can update my solution. So xk is xk minus 1 plus new k pk. So this is my non-stationary iterative method. I want it to be in that form. So I just needed the correct search direction and the correct parameter to multiply it by. And now all I have to do is update my residuals, just like in conjugate gradients. So each residual can easily be expressed in terms of the previous one. So I have rk plus 1 and r hat k plus 1. But actually, I have a second matrix vector product, unfortunately. I need A transpose pk hat. A pk hat is right here. I computed that earlier. And then, oh, is this off screen?
No, you're good. You're
okay.
good.
Well, I only have one step left.
You're fine.
Yeah.
You can say it. You're fine.
I'll bump up my iteration count, and that's the end of the algorithm.
You just can't write behind that eraser right there.
Pretty much.
Oh, this?
Yeah.
Oh, okay.
That's pretty much the level.
Well, that's good. Okay, so if you compare this side by side with conjugate gradient, you'll see it's almost exactly the same. It just looks like certain steps are duplicated because you have these two sets of first search directions and residuals going. The problem is this algorithm by conjugate gradient, also abbreviated as by CG, is numerically unstable because unsymmetric Lanczos is numerically unstable. So BiCG in its original form that I've described it here, people don't really use it. However, there is a modification of it called BiCG stab that was developed to try to fix the deficiencies in biconjugate gradient. It's still not great. You don't see the same kind of really rapid convergence that you do with conjugate gradient for symmetric positive definite. However, because it's based on short recurrence relations, it is quite efficient on at least a cost per iteration. So it does have a, so pick your poison basically. If you're dealing with an unsymmetric matrix, you can either use this that's quite fast per iteration basis, but doesn't have that lightning fast convergence like preconditioned conjugate gradient does. Or you can use GMRAS, which does cost more per iteration, but it's more reliable. It's more robust. You have greater assurance of convergence because you know you're making it residual as small as you can from iteration to iteration.
I have a question.
Yeah.
So in this last line where you're calculating r hat k plus 1,
Yeah.
you use UK.
Yes.
So UK though has the old k vector in it.